Hello, everybody. It's good to see everybody who's here. I think we got 19 of us here today out of the 21. So I'm getting started a little later than what I think I should, but we'll be okay. Today, what I wanted to do was open up the floor to questions that you might have, and to also maybe go over a few things with you that's been occurring in our video lectures of late. And before I open up the floor, let me make this comment or two. It looks to me that we're going to have a total of 34 videos. That's the class. Yeah, that's what I think too. I'd like to get done. Whatever you're thinking, I'm thinking too. So I have done 32, and the 32nd one, I don't think I've uploaded yet. I think I'll do that just after this session is ready. Yeah. And then I probably won't do one until next week. We're teaching 2 classes, so I'm going to be concentrating on the other class. So, as you might say, about dang time. So that's what I'm going to try to do. But we have a homework assignment that had 7 problems to it, and originally it was due today, and I had pushed the deadline back to Thursday because I had written some problems that were not well written, and so needed some corrections. And I appreciate those of you who looked at things and said, wait a minute, what about this example? Or these symbols aren't involved in the problem, except right here at the end. Why are they mentioned here? So I want to thank everybody for noticing those problems, those difficulties with what I had submitted, and I'm sorry about that. But I want to start with opening up the floor to say, does anybody want to see something or have any questions about the homework? Number 6 was asked about. Okay. Well, Melissa, so let's look at, I know this is the one having to do with the boundary?
Yes.
Okay. So, so I think, as an example, how about I do this? I'll do a few things. So first of all, let's start off with this example. Let's let S of n, so I'm going to do something different in the problem. S of n and T sub n be 2 bounded complex sequences. And what we mean by complex is that the output values, the terms of the sequence are complex numbers. Okay? Let's show that, how about S of n times, I'm not times.
That'd be great. That would
Plus
be
T sub n. I'm not finished. We'll get to it. Okay? But let's start off with this. So this is a bounded sequence. Okay, so some students, some of you, whatever we want to call ourselves, I'm a student too, I'm still learning lots. Some of you had said, well, what does this have to do with convergence? Nothing. The word convergence isn't up here, okay? And if you're bounded, doesn't mean that you're convergent. If you're convergent, you are bound, okay? But the reverse order doesn't go. And I had showed that through an example in one of the videos. One of the simple sequences that we've looked at as examples is -1 raised to the n. That's a sequence of real numbers that just bounces between being 1 and -1. And that is a bounded sequence, but it's not a convergent sequence, okay? And so, here we want to show that this is bounded, and we're thinking of the usual metrics on the complex set of complex numbers that's involved. That's that sometimes we put double bars or single bars, absolute value. On the test, for those of you who took the non-makeup test, okay, so almost everybody in here, that was one of the questions on the test was to define absolute value of the complex number. Okay? So here, that's what we're talking about. It's the difference of 2 complex numbers inside absolute values of a metric. All right, I'm talking too much. So here's what happens. We want to show, so I'm going to use the definition of what it means for a sequence to be bounded. We want to show that there exists a complex number, let's say, a p element complex number, and let's say an m greater than 0, such that the distance between S sub n plus T sub n and P will be less than m, and that's for all n element of the natural numbers. Okay? So that's what we want to show. What am I writing down? What am I using? What am I thinking we need to use to get the conclusion of what I'm being asked to do? What is this? It's the definition of bounded. That's what it means, Dennis, for it to be bounded. Is that okay? That's what I got to show. Is that all right, Aaron? So the definition gives me a verifiable means to show that a sequence is bounded. Okay? What's it mean to be bounded? Hey, there's some point out there that every term of our sequence, its distance from that point is less than a number, a one number. Okay? That one number, m, is not changing. Okay? Some number out there, and there might be more than one number out there, more than one number m, but we're saying there's a specific m out there for this one. And there's a specific p for this one. Okay? Well, what do I have to work with? What I have to work with in the assumptions is that S and T are bounded. And so, since... Oh, yes. Thank you very much. That's right on. How about that? Since S sub n and T sub n are bounded sequences, then there exists, let's say, a P1 and a P2 and an M1 and an M2 such that the distance between S sub n and P1 will be less than M1 for all n elements of J, and the distance between T sub n, and this should say M1, and P2 is less than M sub 2 for all n elements of J. Is that all right with everybody? That's what I have. I don't know how that's going to help me create the M that I'm looking for, and I don't know how it's going to help me create the P that I'm looking for. Is that all right with everybody? I'm going to try some things. And here, what this means is, so for all n element of J, what I'd like to tell you, this is what I'm thinking. So I'd like to let you in on what I'm thinking. Not that everything that I think is beautiful, but it's something to try, maybe. Okay? What I'm thinking is this is too abstract. Maybe we should write it down in terms of what that metric is. So that metric was the absolute value. Is that okay? Mm-hmm. So that's going to be equal to the S sub n minus P sub 1 inside absolute value is less than M sub 1, and I'll just write right here, the T sub n minus P sub 2 inside absolute values is less than M sub 2. Is that okay? Okay. Thank you very much. That's perfect. I'm getting away. Yeah, it's perfect. Oh, the sports. I don't believe in those. I don't tell you. People were nice to me as a student. People were very nice to me, but I didn't get bonus points. This has just never happened. So abused students become abusive professors. But people were lenient in terms of giving grades. Look at the grading scale we're using. Okay, so Melissa, do you have a kind of a guess of what Hagenacher raised? It's something just to try for the P in this situation, or something maybe to try for the M. So remember, the P was for the T sub n, or S sub n plus T sub n.
Right. I was thinking that you could use your M sub 1 plus your M sub 2
for
to
the
be your M.
Maybe. That makes sense. And then the, maybe something with that. And then the what do you think the P?
My P I thought of as my P sub 1 plus my P sub 2.
Because we are adding the sequences together, that makes a lot of sense to try that. That doesn't mean just because we try that it's going to work. There's nothing wrong with trying something that doesn't work. Okay? It's beautiful when you try it and it works. But just because it doesn't, we try something else. Okay? So here, let's note that the distance, this is what we're trying to get, between S sub n and T sub n, minus P sub 1 plus P sub 2. Let's look at that. Okay, let's see if it's less than a number for all n elements of the natural number. Let's see if that's true. Okay, well this guy's going to be equal to S sub n minus P sub 1 plus T sub n minus P sub 2. Okay. Well, one thing that's written in the problem is this absolute value is the square root of the number that we're looking at times its conjugate. That's right. Somebody said the right thing. That's right. And I've written that in the problem, but somebody came by and said, well, is that something we should use? No, I wouldn't use it. What we've used that for is to prove facts about the absolute value. So if you go to chapter 1, you got some facts about the absolute value. One of the things is, if you take the absolute value of two complex numbers being added together, that's less than or equal to... Absolute value of two parts. Yeah, that's right. So this is less than or equal to S sub n minus P sub 1 plus the absolute value of T sub n minus P sub 2. And then by assumption of S sub n being... the S sub n is bounded. This P1 was the one that if you subtract and take the absolute value, it's less than M sub 1 plus another guy's less than M sub 2. And that would prove it, Melissa, because there's the P that works, and you gave the right suggestion. Okay? Okay, why didn't we have that one? Yeah, instead of the one we asked. Okay, so we weren't asked that one. So we should look at the one that we were asked. That's next. Is that okay? Might as well. Don't stop him. Thinking, my God, looks like he's going to do the problem. So let's look at another problem. Let's say this. Suppose S sub n and T sub n are complex bounded sequence. So S sub n times T sub n is a complex bounded sequence. So that's our homework problem. And it sounds like, Melissa, I suspect it doesn't sound like, that you would have tried what we tried for this plus. Is that correct? What did you think the P was for S times T?
What I did was I went ahead and multiplied the definition of the distances for the two bounded sequence together. So I had those two absolute values.
Yeah.
And we had a theorem in class that said we can multiply So you can take those two absolute
Yeah.
values, club together, and put them into
One absolute value, yeah, that's right.
And then I FOILed that.
Yeah.
And what I was left with was S sub n times S sub t, which is what I wanted, that's
Yeah.
what I need, minus all this stuff.
And you had to work with all that
And
stuff.
I'm stuck at all that stuff.
Yeah, and it might be that that's an okay way to go. There's something to try.
Yeah.
But a lot of times if you get stuck, okay, you might say, and this is hard for lots of us. It might be to say, let me try something else. It's hard, Melissa, to let go of an idea for lots of us. We'd like to say, how come this doesn't work? And we get obsessed with it. You know, how come I can't get this yet? And one of the things that makes good mathematicians, I think, are being obsessed. They're to say, I'm not letting this go. I'm going to keep after it. But we want to get the problem done, and we want to get it done so that we can move on to get to another problem. Does that make sense? And so sometimes being stuck at one particular thing, trying one thing that isn't leading anywhere, can be detrimental to us. So we try something else. Okay? Well, here, this is something maybe worth pursuing. It's that multiplication. I understood what you said.
Yeah.
And I don't think that I think you might be able to do it that way. As a matter of fact, I think there's a theorem that we prove that has something like that involved. But what I would do, I think, yeah, that's better. What I would look at is this. Okay. Well, since the same thing, S sub n is bounded. There exists, let's say a P1 element of complex numbers such that something that we had this absolute value of S sub n minus P sub 1 will be less than M sub 1 for a particular. So there exists this P sub 1 and M, I should say, greater than 0. M sub 1. Similarly, since T sub n is bounded, there exists a P sub 2 element of C and an M sub 2 greater than 0, such that T sub n minus P sub 2 is less than M sub 2. And I think the natural thing to do is to try again. That would be the point that the S sub n times T sub n don't get too far away from, would be
P or M.
well, that's the distance that we're going to be less than. What's the point that you might try?
P1, P2.
That's right. The multiplication. Is that okay? It seems kind of natural to think that. Is that all right? Let me say this. Why does it seem natural? Look, we're saying the S sub n's are relatively close to P1. We're saying the T sub n's are relatively close to P2. So doesn't it seem like S sub n times T sub n should be relatively close to? Yeah, doesn't that make sense to everybody? That's what should be happening. Okay. And so let's examine that now. So that's what I'm thinking about. So I'm thinking now, the S sub n times T sub n minus S times T. S times T. P1 times P2. I'm looking at that. So that's what my guess is I can make this be smaller than a particular number. Okay, well, I don't know. It's kind of hard to work with unless there's not something there. And that's why having what you said generates more there with something maybe we can work with. I don't know. But I'm going to generate something more. What I'm going to do is I'm going to say this is the same thing as the absolute value of S sub n, T sub n. And let's try minus P sub 1, T sub n, plus then P sub 1, T sub n, and then here's minus P sub 1, P sub 2. And all I'm doing is just sticking in this quantity, adding it and subtracting it. Okay? Same quantity. I'm going to look at that. Everything else is the same. I added and subtracted the same quantity, so I didn't change it. And T sub n maybe for a fixed n. Okay? Now, it doesn't matter. For any of the n's, we can do this. All right, so that's something that's true. Is that okay with everybody?
You could split that.
And then you can split that. You can split it using,
Less than rule addition.
yeah, that's right. It's something that Aaron said, I think, earlier today. So let's go ahead and do that. Okay. That's what I'm talking about. Okay, so here, I will say that's less than or equal to, here, S of n, T sub n minus, I can't see, is P sub 1, T sub n?
Yeah.
Okay. Plus the absolute value of P sub 1, T sub n, and then it was minus, what was this? This was,
Piece of one, piece of two, right?
yes, that's right.
Back and right on.
Yes, and so here, we can take out, it looks like a T sub n. And it would be, okay, so I'm going to do this a little slowly. T sub n, S sub n minus P sub 1 plus, here this is going to factor out a P sub 1, and then a T sub n minus P sub 2. Is that okay? And then, Melissa, remember you had that, you told it to me just a few minutes ago. You had that rule, if you take the absolute value of multiplication, that's the,
It's the absolute value of multiplication means you can split them.
tell me what to write.
Oh, you have the absolute value of T sub n times the absolute value of S sub n minus P sub 1 plus the absolute value of P sub 1 times the absolute value of T sub n minus P sub 2.
Okay. Now, remember, I want to make this be small. Does that make sense? Less than a number. I don't know what number out there. I'm trying to generate that.
Can't you just, never mind.
But wait a minute, what do you think?
Sn minus P1 is less than M1,
That's right.
and that's less than M2.
All right. Excellent, Christy. So here we got T sub n. Then S sub n, this is going to be replaced something bigger than it. That's M1. And then plus, here this is just P1, absolute value. Well, that's just a number. Is that okay? And then here this is less than M sub 2. Oh, this is great. Is that okay with everybody?
That's what you need, isn't it?
Well, here, you know, that is right if you could say this. So let's, I was going to do more work. But here you could say we pick a particular, let's see, do I pick, let's see, if I pick a particular T sub, no, I can't. There's still more work to be done. You see, to pull out this T sub n's, this T sub n here is really not a fixed T sub n. Is that okay? Okay? And so we still have this absolute value of T sub n's, and it might change depending upon the,
Depending on the term in the sequence.
yes, and so really there's one letter that it would depend on.
And
N. Somebody said the right answer. N. Is that okay? So the absolute value of T sub 1 might be different than the absolute value of T sub 2. So you don't have a fixed number out there yet. Does that make sense? So now we worked on all this stuff. We got the M sub 1, M sub 2, but we still got a bottleneck here in terms of getting the solution. And that I got to put in a number bigger than this guy, if there is one.
M2.
Well, M2 is the number that's bigger than T sub n minus
P.
P. So I can't put in M2 just yet. Your idea, Christy, was nice. Not quite right, okay? But at least it's thinking about the right thing.
M2 plus P2.
Okay, so something,
Value of P2.
well, that, I think that works. And that's something that we've looked at a little bit, okay? That where we would bound something before, like we did in, there were some times that we talked about K cells, and that we would get bounds for the K cell, or creating the K cell with bounds on the absolute value of things. So here's what I want to tell you. Since, so let's talk through it. Tiffany, we're getting close to having the whole thing complete. On top. Since T sub n minus,
P2.
yeah, it's P2 is less than, it was M2, wasn't it? Okay, then, what that says is that I think this right here is a real number, okay? So we can think of it as it's going to be is going to be bigger than, let's write this down, minus m sub 2,
Be less than.
less than, hold it just a second, so I need to think about it before I go any further. I'm going to make some space here.
Isn't it, wouldn't it be T sub n, absolute value of T sub n minus the absolute value of P sub 2?
I don't know yet, Annie. It's something to think about. It could be that, okay? Here, I'm just going to write this right now. I don't know if this is going to be beneficial, so I might write this, and then you guys get to cross through it, okay? I don't know if this is perfect yet. But one thing I can say is that minus m sub 2 is going to be less than, because m sub 2 is bigger than 0, it's going to be less than T sub n minus P sub 2, which is less than m sub 2. Is that all right?
I mean, what's in the middle is gonna be bigger than the subtraction of splitting it up.
Okay, so here's what was said. Is it true that T sub n minus P sub 2 is going to be, you said less than, greater than? Yeah, but the greater than is not maybe not what I want.
Or equal to.
Yeah, well, let's think about it for a second. What I'd like to have is the T sub n being bounded by something inside absolute values. Is that clear with everybody? I just want the absolute values of T sub n. Well, here, let's do this. Let's say that this is minus m sub 2 is less than, I don't know. Let me think here for a second, okay? So I'm thinking of maybe I could add P sub 2 and subtract P sub 2. Let's see. Oh, just a second. Let me think.
They should be. Why are the absolute values?
Can we get rid of
still
absolute
there?
values?
Why are they still there?
Well, the reason that they're still there is first of all, if you don't have them there, you don't have a real number. And we can't compare. We don't have a less than on the complex numbers in terms of this, okay? So, I mean, what does it mean for 1 plus I to be less than 3 minus 2I? We don't know. Does that make sense?
Yeah.
So we got to make sure we know what settings we're talking about. Okay, so here there is something. Let's see. Is this the case? Let's try to make some comparisons. I'm going to think about things. So how about the absolute value of T sub n minus the absolute value of P sub n? Let's look at this guy and compare it somehow to this guy. I want to compare those two. Now, I know what you might be thinking, or I have to say, well, how were we supposed to come up with this? We played with it, okay? And today's a day which I was going to help in some sense. So, I want to compare these two, okay? I don't know, maybe we're trying to compare them together, I don't know.
That's P sub 2.
Yes, so here, yeah, let's put P sub 2. Can we compare them? It seems like they're both numbers, they're both real numbers, we'll be able to compare them. Seems maybe there's something we can do here. Here, let's see, the absolute value of T sub n, what's it equal to? It's equal to the absolute value of T sub n plus, let's make it minus, minus P sub n, P sub 2 plus P sub 2. Let's look at this for a second. That's a true statement, right?
Yeah.
Okay. And so here, this is going to be less than or equal to the absolute value of T sub n minus P sub 2 plus the absolute value of P sub 2. Is that okay with everybody? Okay. And so that says that T sub n minus the absolute value of P sub 2 is less than or equal to the absolute value of T sub n minus P sub 2. Isn't that right? Okay. Now this is a real number. Is that all right with everybody? And this is a real number. Is that all right with everybody? Okay, so I've got that statement. And so I'm gonna leave that as is right now. So I'm gonna do a little bit more. So this is a true statement. So let's look at this statement. Also, the absolute value of P sub n is equal to, let's look at that guy.
Hey, Dr. Wade,
Yes, sir.
don't we have enough information to go on without doing the P sub n? Because we have T sub n bounded inside of its own absolute value. And we can just put it less than or equal to what's up there, which implies that's less than M2.
Yes, but we have it bounded below.
It needs to be bounded above.
Yes.
Okay.
It needs to be bounded above.
Okay.
Yes. No, you didn't ask anything wrong. It's worth looking at. Okay, so let's look at this P sub n. Well, it's equal to, isn't it P sub n? I'm going to do the same thing. Isn't it P sub n? Here it goes again. P sub 2. Okay. Isn't it P sub 2 minus T sub n plus T sub n? Isn't that right? And that's less than or equal to, here, what would I write? I'd write down P sub 2 inside absolute values, or, I'm sorry, minus T sub n, and then,
Plus absolute value T sub n.
okay, and then, so what we get is that P sub 2 inside absolute values minus the absolute value of P sub n, that's going to be less than, it's going to be less than what? It's going to be less than or equal to P sub 2 minus T sub n. Is that okay with everybody? Let everybody look. That's a mess. Is that okay? It's true, I didn't write anything wrong. I'm just asking you questions about it.
You can multiply this out by -1, can't you?
Yes, that's right. And here, first of all, this is the distance between P sub 2 and T sub n. Isn't that the same thing as the distance between? Okay, so here I can say, that's right, that's what I was looking for. So P sub 2 minus T sub n, each individual inside absolute values, is going to be less than or equal to T sub n minus P sub 2. And so then there was a multiplication by -1. Is that okay? And so this says that, this would say that the absolute value of T sub n minus P sub 2 would be greater than or equal to minus T sub n minus P sub 2. Is that okay with everybody? And then there was somebody said, yeah, there was something, no, I think this is okay. Is that okay with everybody? We're almost there. Okay, what does that tell me then? So here, so what we have is, I think, minus the quantity T sub n minus P sub 2. That's this part. It's less than or equal to absolute value of T sub n minus absolute value of P sub 2. That's it right there. That's this guy. I'm just rewriting that statement. But look, right here, we got that quantity that I've just written right here is less than or equal to T sub n minus P sub 2. So look, when you have some number, that's a real number, that's sandwiched in between a positive number and its negative version of it, what does that tell you?
That is,
So if C is, if we're talking about numbers sandwiched in between -3 and 3, how could you rewrite that?
Absolute value C. The absolute value of C.
Okay. So that says that the absolute value, I don't know if this is so. So this says the absolute value of T sub n minus the absolute value of P sub 2 is definitely less than or equal to P sub n minus P sub 2. That's what I got, but that's less than or equal to that.
We need to be bounded above.
Yeah, it didn't work. Is that okay with everybody? I mean, it's not okay, it's not you. Yeah. But it didn't work, is that all right? Didn't work.
I think the reason it didn't work is because when we did the piece of 2 and we changed it to a negative, we inevitably just changed it back to what we got when we did the T sub n part, didn't we?
I didn't follow, Aaron.
When we did the T sub n, we got that, the apps, where is it at?
Here's what I'm looking.
Dr. Whitaker.
Yes.
On video 19, the proof of theorem, of the theorem from part C, you broke apart. So this would be, instead of keeping going with this, go back to that, back to the beginning,
Okay.
and change S sub n, T sub n minus ST equals to something else. So that we add and subtract.
Something else, you're saying?
No, yeah, 2 different pairs.
2 different pairs.
Instead of the 1 pair that you did, so that.
Yeah, and so there was something, that's right, we did look at a different proof where something was involved
That
here.
was on convergence, but this follows very similar.
Okay, so that's nothing wrong, that's a good thing to do. So this was something to try, it didn't seem like it worked, and you know how I said it's hard to let something go?
Yeah.
I'm not quite ready to let it go. Give me just a minute or 2 more. But you're right, you're right. But let's look just for a second. I did this. I want just a minute or 2 more. You guys can follow along and see what happens. But you're right, there was something in the previous video where we could return. Okay, okay, so, let's see. So I want to say something about this bounding T sub n. Okay, so what is, probably very silly. Isn't this the same thing as, equal to the absolute value of T sub n plus minus P sub 2? Isn't that less than or equal to T sub n plus the absolute value of minus P sub 2? Isn't that true? Isn't that true? And so isn't that less than or equal to T sub n plus P sub 2? Is that okay? No. And you know, here I have something bigger, but you know, I want to stop for a second. I said, oh, we want something bigger. I'm not sure about that now. I'm not sure about it. So wait just a second. So this says that if this guy is less than this part, okay, that's what it says. I don't like that. I don't like that.
I was gonna say, if you subtract something that's bigger, then when you get, the end result would be something smaller.
Something bigger than what? When you subtract from what?
If you're subtracting P sub 2,
Yes.
since the quantity absolute value T sub n plus absolute value P sub 2 is larger than the absolute value T sub n minus P sub 2, when you
It
subtract,
went a little too fast for me. So here, say that again.
since the quantity that's there to your right
I will.
So here, T sub n
is larger than the absolute value of T sub n minus P sub 2 all inside. Wouldn't that mean if you subtracted the P sub 2 over to the M2 that you would not be able to ensure that T sub n is indeed still larger.
So here, this would say T sub n itself is bigger than or equal to T sub n minus P sub 2.
Minus the absolute value of P sub 2.
Yes, but we want the absolute value of T sub n to be
Less than.
less than, that's right.
So we should have went with the smaller bound, right?
Yeah, I think that's right. So what did we have before? What was it? It was the,
It was the absolute value of T sub n minus the absolute value of P sub 2. I believe.
what did we do? So what did you say? This was it less than or greater than? I forgot.
It was less than or equal to absolute value of T sub n minus P sub 2.
Okay, and so this said that T sub n minus P sub 2 was less than this guy right here.
Yeah.
Okay, so let's stop there for a second. Okay, and so this is definitely less than m sub 2 minus absolute value of P sub 2, isn't that right? Yeah, because this is less than, no, it's not. No, I don't have anything to say here. So this is definitely going to be bigger than, hold it just a second.
Can't you just go from there and say that the absolute value of T sub n would be less than m2 plus the absolute value of P sub n, P sub 2?
So here this says the absolute value of T sub n is less than m plus the absolute value of P sub 2. Yeah, exactly. That is right. Yeah, there's nothing wrong with what we just said. And so I have a bound for it. That is right. That is right. That is right. Yeah, so let's go through it again. That's right. You put your seven right. So let's start at this part again. Yeah, that's right. We got it. I think we got it. Let's check the details again.
So you found the bound for T sub n.
Yeah, that's what we want. It's bound for T sub n. Okay, so I'm going to go over here again. Let's go through it again. So you wrote this down. Let's look at it. Okay, so we wanted to compare, let's look at T sub n inside absolute values. That's equal to the absolute value of T sub n minus, we don't need it. It's beautiful. Minus P sub 2 plus P sub 2. Write something down, John. This is correct. We're okay with that? All I'm doing is adding? 0. That's right. This is less than or equal to T sub n minus P sub 2 plus the absolute value of P sub 2. This is less than, what's this distance less than?
M2.
M2 plus P sub 2. I got a bound for T sub n. It's just that. Is that okay with everybody? That's it. So when I have here, what I have here, I would write the following. So this is correct. I'm going back to where we were. Then I'd say the absolute value of T sub n, which equals, I'm going to write this again, which equals to T sub n minus P sub 2 plus P sub 2 is going to be less than or equal to T sub n minus P sub 2 plus the absolute value of P sub 2, which is less than M2 plus P sub 2.
Dr. Ware, should we put note, like instead of then? Because that doesn't lead from the previous step.
It does lead from this step because I'm using it right here.
Okay.
That's the only reason. But you can say note this absolute value of T and then just have the reader understand I'm replacing this with this, and the reason that's true is because of this. It's okay. It's okay to say no. Okay, that's right. So, where we started, where did we start? We started with the S sub n, T sub n, minus, what was it?
P1, P2.
P1, P2, that's right. Okay. We had that it's going to be less than or equal to this S sub n, T sub n, minus P1, Tn, plus P1, 10 minus P1, P2. I'm just rewriting the work we have here, okay? Which we get is less than, we get all the way down to, I think it should be, less than, because we're making substitution here. It's going to be T sub n, M sub 1 plus P sub 1, M sub 2, but then we just have a bound on this guy, which was M sub 2 plus P sub 2 plus P sub 1 times M sub 2. Is that okay with everybody?
I'll agree. Don't we need an extra M1 after that piece of 2 and the absolute value?
So here, yes. So this needs to be in parentheses, and then I forgot the M1. Yep, sure did. So I'm replacing the T sub n by something that it's less than. So the next quantity got bigger. Is that okay? Well, listen, Evan, did you find an easier way to do that?
Yeah, it's from your thing in lecture 19,
Yeah.
how you rewrote S sub n times T sub n minus your two values, your P1 and P2. You rewrote it as a really long thing, but it ends up just being S sub n minus Q sub 1, or S sub n minus P sub 1 times T sub n minus P sub 2, which is, then you could split them apart. It's the two sequences multiplied, which means your M1, M2 can be your M, and your Q1, Q2, or P1, P2 could be your P. So it does work out that way. It's much easier.
Okay.
So it's in lecture 19, Evan showed me.
Wonderful.
It works out wonderfully.
Yeah, I think in that one, that was approved, Evan.
That was all convergent.
It's
About convergence.
But it's just about
Yeah,
adding
no,
and
that's perfect.
subtracting.
We use the same technique. That's what we see in the techniques.
It's exactly the same technique as the addition problem.
Instead of adding one pair, you add two
Two
pairs.
pairs.
Right. Beautiful.
So,
But I want to tell everybody this thing too. It's nothing, what we did here, nothing wrong with it. It's another way of looking at it. And we got stuck, or I got stuck, and that's normal. Okay? It's normal. The unnormal part, actually I think this is, it's unnormal to keep going. But it's what we got to do, because we got to get the problem. Does that make sense?
Mhm.
It's not normal. We want, it's kind of funny. We want to be better than normal. The normal thing to do is say it didn't work, and well, to heck with that. The better thing is to say we keep going. Does that make sense? And so that's what we're looking to do. So anyway, I fumbled around a little bit there and said, wait a minute, got something, go back there. That's right. Need a little help? Yeah, there's nothing wrong with that. Good. Is that okay? Does anybody have questions about what I did? When I write the solution, this is what I would do. But there was something else that Devin was talking about from the video lecture. Same technique. It works too, it sounds like. I didn't try it, but it sounds like you guys are convinced that it works for this problem. What else would anybody like to see done?
I'm on number 5.
What's 5 say?
It's, coaching. You have 3, the coaching and arm.
Yeah. So, Evan, the reason, Evan, let me not go so quickly mentally from one thing to another. But one of the things that I think is something to step back, if we have time to step back and say, okay, good, is that the problem we just worked on, you said it's like something you did in video 19. So we learned that and we apply it here. In my case, up here in front of you, I didn't do that. I fiddled around, tried to do some other things, and eventually we got it. Nothing wrong with that either. Okay? We're trying to get the problem. For not 19, for the problem you're asking me about, for the problem that you're asking me about, there were some times in working with RK about maybe convergence that we'd have something, I said about convergence, here we're going to be talking about quotient. That in RK, when we talk about convergence, there was times that we had something epsilon over the square root of k. You look back at some of the proofs, okay? I said, I don't remember what he's talking about. If you'd like to look back at some. And one of the things that this problem gets us to do is to concentrate on that aspect of certain of those proofs that involve the square root of epsilon over the square root of k. So here's the problem that Evan is having us look at, asking about. So this was problem 5. It says, let A sub n, B sub n, and C sub n be quotient in R. So each one of these are real valued sequences that are quotient. That's what we're saying. Let x bar sub n equal to the sequence, let x sub n bar be equal to A sub n, B sub n, C sub n. Show x sub n bar is Cauchy in R3. Well, what does it mean to be Cauchy? There's a definition. I'm not talking about the idea. I'm talking about the definition. The idea is that there's some spot in the or that the terms of the sequence eventually get really close to each other. That's the idea. Is that okay? But that's not the definition. The definition incorporates that idea. But the definition is written in such a way that it gives us kind of verifiable meaning. So, Evan, do you remember the definition to be Cauchy? What does it mean for a sequence in a metric space to be Cauchy?
There exists epsilon greater than 0.
I wouldn't say that's the first term. Try again. You're right about epsilon greater than 0, but I don't think it's there exists.
We need a
It's
For all.
for all epsilons. Okay, so here. So I'll just write this down. Let's call it T sub n. It's a sequence in a metric space. Sequence in the metric space. Okay. T sub n is Cauchy if for each epsilon greater than 0, there exists, what was it, Kristen?
there exists an n, big N, and J.
Natural number, such that
Greater or equal to n.
the distance between
Between CNN and CNN is less than epsilon for R0 for all.
that's the definition. Is that all right? So that's the verifiable thing we've got to use. Anybody else? So here, I want to show that x bar sub n is Cauchy. Okay? So I got to apply this definition somehow. So I'll put myself in this definition. It says for each epsilon you give me, there's an n. Well, I'm going to start off in this proof by saying let what do I have to do to show that this x bar sub n is Cauchy? I have to say that no matter what epsilon you give me, there is an
There's an N.
there's an n.
J.
Is that okay? That's what I got to do. So no matter you give me an epsilon, I got to produce the n. That's what I got to do. Is that okay? So one thing that's important is for us to know what it takes to satisfy what we're being asked to do. So that's what we got to find this n. We need an n. such that for all n and m greater than or equal to big N, the distance between x of n bar and x of m bar is less than epsilon. That's what we got to do. You might remember earlier I said to Melissa, I said, look, what I'm thinking is, this is too abstract. We're talking about metric space definition, but here, Julie, we know what our metric space is. We're talking about x, so x bar. Where's x bar living, Julie? Say it again, you're right. Angie said the right thing. She says R3. R3 is a metric space. And when we say it's a metric space, we got an idea, or we know what we mean by usual metric on it. I know what I mean by usual metric. What do we mean by the usual metric on R3? What's the usual metric? What is that? So I'm going to go over here. Absolute value of, yeah, I guess I'm not going here. I guess I'm going right here. What is the absolute value? What is this distance? You said the norm. You're right, Melissa. So D on R3 of x of n bar, x of m. So this is where, Aaron, you might say note. Note this guy right here. What we're trying to make small, be less than epsilon. What's it equal to? It's equal to this. Well, I think that's a little too quick for me. So here it's the x of n bar.
Oh, it's x of n bar minus x of n bar, and then
And now we'll get to the a's, b's, and
now
c's.
you can replace them with the a's.
Okay, now wait a minute. How do we replace them, Melissa?
A sub n minus, oh, sorry.
Yeah, go ahead.
A sub n minus A sub m, maybe, I don't know.
Okay, well, listen, so that's going to be involved. But I'm going to stop us all for a second, Evan. How is this, well, you know, you're right. So it's the norm of this. What is x of n bar minus x of n bar? It's a 3-tuple. Got 3 coordinates, if you want to think of it that way. So it's this guy, comma, what's next? That's right. Okay. I was going a little too fast then. I was trying to jump to something. Okay. So this is nothing more than a point in R3. Is that okay? It's got 3 numbers, real numbers right here. Is its coordinates. What's the norm of something in R3?
The square root of the differences squared. When you add the differences.
Okay, that's right, Melissa. You said the right thing.
Squared.
That's right. We don't know it's less than x. So we need to show such that we won't make this guy be less than epsilon. Such that for all n and m bigger than or equal to big N, the square root, this guy right here, a sub n minus a sub m, that's an m there, squared, that's an m, plus b sub n minus b sub m, to be squared, plus c sub n minus c sub m, to be squared, is less than epsilon. That's what I want. We need an m, so this is going to happen. I'm again trying to write down what it takes for me to solve the problem. We don't have this. Okay? So I want everybody to know we just kind of reduce the problem somehow.
Can't we square both sides because of both positive?
So that would say what we want. Yeah, that's right. That is right. We want this to be less than epsilon. Here's what I'm thinking. You're right. So that's something we can do. I'm not going to do that. But that is something we can do. What I'm thinking is that, what is this saying? We want this to be small. What's on the left-hand side? That's what we're trying to say. We want that to be small. How are we going to make it small? Well, I'd like to make each one of these parts be Small. How come I can make each one of these parts be small? Because they're Cauchy. And so, maybe with the Cauchiness, I can make each one of these parts be small. Is that okay? Is that all right?
Yeah.
That's the idea. Evan, unlike the problem that Melissa asked me about, 6, I've done this problem. So we're not going to fumble around so much. But I don't think the fumbling around is a beautiful thing. I don't. So I've heard plenty of people as professors and teachers say, you know, when you get the students get to think, see you think. I think it's much better to have thought, but I don't think it's a disaster for me to have to work in front of you. I don't think that. Okay? But I think it's much better to be prepared. So I stopped at problem 5. That's where I got to before class. I didn't get to 6 yet, so I would have thought, but I didn't. So I wasn't prepared for it. But I knew it could be done. And we eventually got a version of the solution. We got a solution for it. Might not have been the best one.
We got some. You know, like you work the 5 to ask about.
I know how to do 7 too, so just in case you want, I know how to do them all. All right, so that's what we are. So here's what I'm thinking. The question is how small do we want to make each one of these? Okay? Well, here's what I kind of got in mind. We'd like for them all, maybe all to be less than the same thing. So it's a square. We want this square to be less than epsilon. Is that okay? That's what I want. I ain't got it. That's what I'm thinking. And so what does each one of these things have to be? Well, it's like what was said. It's square plus square plus square. Whatever we're putting here. We're going to put the same thing. Could put x. Is less than epsilon squared. Is that okay with everybody? So this means 3 times this square has got to be less than epsilon squared. Or that means that this square here has to be... Okay, that's what we have. Okay. What's our square? Our squares, each one are like a sub n minus a sub m to be squared. Is that okay with everybody? So really, we'd like for a sub n minus a sub m to be squared to be less than epsilon squared over 3. That's what I'd like. Okay? That's what I got in mind. Okay? We'd like that. These are all we'd like. I don't know. I ain't got it. Kevin, I ain't got that. That's what I'd like.
Wouldn't you want it to be less than, not over 9?
Well, wait just a second. I mean, being less than over 3 might be good enough.
Oh, yeah. Okay.
So here, what do we get to control? So, I mean, that's what I want to have happen. What do I get to control? Well, here's what I'll do. I'll say, since a sub n is Cauchy, then that means there exists, we've been given an epsilon, okay? So there exists, even if I haven't been given an epsilon, no matter what positive quantity you give me, there exists an n for that particular positive quantity, such that's an element of j, such that for all n and m, bigger than or equal to this big N, the absolute value, that's the usual metric in R. Remember where this guy lives. It lives in R. That a sub n minus a sub m is going to be less than whatever was given. I'm going to put triangle because I don't know what it is. Okay? I don't know what I'm going to use. Well, wait just a second. Now this is like playing the role of epsilon for this guy being Cauchy. Right there you say it. Cauchy. All right, so here's what I got. What is this guy? What is the absolute value of a sub n minus a sub m? Can I write it in something that I want, which has to do with this guy being squared? What is this guy? Square root of what, Ashley?
The a sub n minus a sub m squared.
That's right. To be less than the whatever here's here. Is that okay? So I can make this less than anything positive. Okay. So that means I would have a sub n minus a sub m to be less than, it would be, to be squared, to be less than delta squared. Okay. Look at this comparison now. Is that okay? What's the delta squared need to be? It needs to be this. Is that okay? So what's the delta? So delta squared needs to be equal to epsilon squared over.
So delta is the square root of epsilon, or it's epsilon over the square root of 3.
All right, so that's the work behind the scenes that gives us an idea. Okay? All right, now I'm ready to put it together. That's the work behind the scenes. So here's what we are to prove. So this is all kind of scratch work off to the side. So here's what we are to prove. So we need this in. That's what I'm looking for. Okay. Here's what I write. Well, since A sub n is kosher, well, there exists, I'm going to call it n sub 1, element of J, such that for all n and m bigger than or equal to big N sub 1, then the absolute value of A sub n minus A sub n can be less than whatever I want. What am I going to be less than? This. Is that okay with everybody? So I'm going to stay with A sub n's for a little while. So that means that the square root, as Ashley told us, of A sub n minus A sub m to be squared will be less than epsilon over the square root of 3. And that's true for all n and m bigger than or equal to n sub 1. Not true for all n and m, just for those. So that says that A sub n minus A sub m to be squared is going to be less than epsilon squared over 3 for all n, m greater than or equal to n sub 1.
Can you say without also generality?
We can do the same thing for the...
B and C.
That's right. Is that okay? So, similar, I'm just going to write it down. If that's okay, I'm going to do the same exact things can be done for the sequences B sub n and... Okay, so let's write that down without the detail, just each statement. What is each statement? So for, I'll say similarly, since B sub n is kosher, there exists, what am I going to write here? N sub 2. Yeah, it doesn't have to be the same N sub 1. Is that okay? It might be a different spot. N sub 2, element of J. Such that for all n and m bigger than or equal to this N sub 2, we get exactly this. Right here. This is the conclusion. The B sub n minus the B sub m to be squared is less than epsilon squared over 3. Is that okay? And then what am I going to say next? Same thing. Yeah, that's right. Look, I'm working over here. Remember, this is the guy that we want, okay? This is what we want. I'm going to leave it up here for a second longer. I'll raise this up. Similarly, there exists an N sub 3 element of J such that what? For all
N and M. And 3.
what can I write?
Less than epsilon over epsilon squared over 3.
Okay. Now, here's what I'm thinking, Evan. You asked me a question. Look, I'm thinking, oh my gosh, for this guy I can replace it. Something bigger, Evan. What can I replace that's bigger than a sub n plus a sub n squared? What's bigger than a sub n plus, a sub n minus a sub m squared? Epsilon squared over 3. So I'm going to replace this guy with epsilon squared over 3. I'm going to replace this guy by epsilon squared over 3. I'm going to replace this guy by epsilon squared over 3. When you got epsilon squared plus over 3, added together 3 times, what do you get? Epsilon squared. And then we're going to be taking and we're going to get, that's it. Is that okay? But there's one more problem. We got to find, what was our goal? Look at what's still written on that right-hand board. We need to find n. What's n? I didn't give you an n.
That's the max of all the three.
That's the maximum of all the 3 n's that we had. Why? So let's stop for a second. Here. Okay. So I'm going to write this down, and then we're going to think through it. So I'm going to let n equal to the maximum of n sub 1, n sub 2, and n sub 3. Travis, you give it a second to catch our breaths. I'm going to ask you a question. Or talking to the class through Travis. Travis, all this work here says you got this sequence. What's the sequence? The sequence is a term, in this case, of real numbers. Okay? You got a sub 1's a real number. You got a sub 2's a real number. A sub 2's a sub 4's a real number. A sub 5's a real number. I'm getting tired. A sub 6. It goes on forever. We're saying there is an n sub 1 element of J such that for all the indices are just positions. A sub 1 is the number in the first position. A sub 50 is the number in this sequence in the 50th position. We're saying there's a spot in the sequence, a position in the sequence, such that from that position on, if you take any term from that position on in our sequence, subtract them from each other, square it, you're less than epsilon squared over 3. Is that okay? So there's a spot for A. It's called n sub 1, such that from that spot on, you get what you want. Is that okay? For B, the sequence B sub n, there's a spot. We call it n sub 2, such that from that spot on, you get what you want. For the sequence C sub n, there's a spot in that sequence such that from that spot on, you get what you want. You want to get all 3 of those things to happen. Okay? So here, if you come over here just to kind of hammer home the point, I hope. Let's say I'm from here over, let's call this 17. From here over, we get what we want. Let's call this 12. From here over, we get what we want. Let's call this 20. From here over, we get what we want. And I said, I want to give you one spot in all the sequence, such that from that spot on, for each one of the sequence, we're getting what we want. If you said the answer was 12, from the 12th spot on, in each one of the sequence, we get what we want. I said, no, we don't, because we stop here at the 12, start at the 12. This first little part, we're not getting what we want. Is that okay? Where do I have to start in each sequence? It's the same spot in each sequence so that I get what I want. The maximum. So we start at 20. From the 20 spot on here, we're getting what we want. We got what we want a little earlier. But from the 20th spot on, we got what we want. From the 20th spot here, we got what we want. But from the 20th spot here, we got what we want. Okay? And if you went to a number that's smaller than that, not in all 3 sequences do you get what you want from each of those starting points. That starting point. Is that okay? So that's why we take the max. Then, for all n and m greater than or equal to n, we have a sub n minus a sub m squared is less than epsilon squared over 3. Also, the b sub n minus b sub m squared is less than epsilon squared over 3. And the c sub n minus c sub m squared is less than epsilon squared over 3. I'm going to erase this, but essentially we've done. So, for all N and M greater than or equal to this big N, the norm, that's what I was working with, the norm of x of n minus x of m, which we know is equal to the square root of a sub n minus a sub m to b squared, plus, I know this is what it is, b sub n minus b sub m to b squared, plus, I know what it is, it's c sub n minus c sub m to b squared. It's going to be less than, I'm going to replace each one of them, of the guys being squared, replace it with something that's big. It's the square root of, what do I put? Epsilon squared over
3.
plus epsilon squared over 3 plus epsilon squared over 3, which equals to the square root of epsilon, epsilon squared, which equals to
Epsilon.
epsilon. Now we want to show this guy was less than epsilon, but it is, because here's our less than. Is that okay? And that's the proof. And it's not necessarily quick or easy, but it's gettable. The proof, Evan, that you were mentioning about for that other problem, it was about to show that the product of two convergent sequences, complex numbers, is convergent. Yeah, I didn't like the way he did it. That's why I was getting away from it. And I didn't go back to look at it anymore. I didn't like the way he did it, so I was trying to get away from it. And that's why we kind of fumbled around up here to look at it. But it does work beautifully, you think? In terms of it's the same? Good. So everybody, Evan's saying, and there's nothing wrong with this, go back and look at the proof for problem 6 if you want to see something, maybe a different way of doing it. Look at the proof when we were asked to show that if you have two complex sequences, each one of them converges, then their product converges. I think that's exactly the proof you're talking about.
Yes.
Yeah, that's right. So if you want to look at that, go ahead. That's an example. Helps you do problem 6. That's technique. Okay, what else would anybody like to ask about here? Yes, ma'am.
Will there be any more homework assignments before the final?
The answer is yes.
How many?
And it's going to be short.
What do you mean by short? Yeah, is this considered long?
Yes. It is. Yeah, it is. Yeah, that's when we got time to work on it now. The days. So we don't have too many days. So I'm thinking 3 or 4 problems. And that I hope are straightforward. And they're going to do with something about limit of a function, continuity of a function, and then maybe 1 or 2 more things. Yeah, I'm probably going to give it to you tomorrow, and probably doing it a week and a half or something like that.
You know when we'll get it, when you do it, so they got what you know.
Yes, sir, I will.
When we get it.
I think you guys are going to get yours early. Okay, I think that I'm almost through with the course. So 2 more video lectures and I'm done. So I know what the course consists of. So I think I'm going to give you probably Sunday wouldn't surprise me. Is that bad?
That's wonderful.
So that's me. It's very biblical, Michelle. He who tooteth not his own horn has his horn not tooth. Okay, that's some nice questions about the structure, of course, and that's important. We need to know. It kind of puts our minds at ease. Go ahead.
One more about that. Dr. Darbo needs to change his. We were hoping your exam would go first on Thursday, so we can see there.
Okay. I don't care.
Say that again?
What's going on?
The question was, could I give you the exam on Thursday? Of the,
Like we talked about with Darbo.
I don't remember the conversation.
I don't know.
Yeah, he has to get his on Friday
He
because
won't be in town.
he won't be here Thursday.
Oh.
so, look, if you want me to write 2 exams, it's easy. If some of you want to take it on Thursday, 1 version on Thursday, that's
It's either
right.
that or we have all 3 on Friday?
Mm-hmm.
Is that what he's saying?
He said Darby was gonna try to
Did you
switch
have this
it
conversation
somewhere.
with the class? Was I sleeping?
Yeah,
I see what you're saying.
You know, ladies and gentlemen, I don't wanna, I know you guys wanna get that straight, because the structures of the classes you're taking is important, okay? You get it straight. I'm gonna give you the exam whenever I'm told to give you the exam. And that's it. And you can be the guys telling me what to do, okay? But whatever you want, that's what I want. Is that clear what I said? So if you won't take it on, I mean, I need a few days. All right. You guys can talk about that afterwards. Let's go. I might have more time than I need to waste thinking about it, not being prepared, so let's get to that. What else do you want to see done? Anybody? Nobody has any other questions?
Well, last night on number 4, some of us were working with.
Yeah.
Majority and back and forth about how to, with the subsequent, showing the order in that, we were not getting anywhere.
Okay. Wonderful, I'm ready. Thank you, Dennis, for asking the question. Thanks for everybody else, Melissa, for asking your question. And people who helped in getting the solution to that problem. And thank you, Evan, for asking your question. You know, as I race the board here, I hear people who are speakers so often. I want to tell you this social comment as I race the board. When people who are talkers, you know, in front of the audience, okay? They'll have a question and answer session. Somebody asks them a question and they say, "That's a good question." What that means is the audience member, the speaker doesn't know the answer. Every time. You ever heard somebody say, "That's a good question," and the answer is? Not one time do I ever see anybody do this. Okay? So yours was a good question, Evan. Your question was, think of it for a little while until we got it. That's the way I feel about it.
Hey, sorry, we were all wondering six.
That's right, and I'm glad it was asked because we got it. Now I know what to write down for the solution. And it's not the only solution. 4. I'm ready. So I'll wait to see more time. Let's go. 4 has to do with the one that had to be rewritten. It says, suppose, they call them S of N's, is an unbounded sequence of positive numbers. Show there exists a subsequence S of n sub k with S of n sub k. We wouldn't say the word converging, okay? We'd say tending to infinity, okay? Is that okay with everybody? We'd say converging because we're thinking of S of n being real numbers, a sequence of real numbers. And infinity isn't a real number, so okay, so it doesn't converge. It tends to infinity. So Dennis, you asked me this question. All right, so here's what I'm thinking. What does it mean for it to tend to infinity? So over here, kind of the setup, I'll write down the definition. For S of n sub k to tend to infinity, that means for any, I don't know what symbol I used in the definition. I'm going to say M here. I don't know that I used M. Do you know? Does anybody know? Could have called alpha. For any M, it's element of R. There exists, I'm going to call it a big L. Okay? There exists element of the natural numbers such that for all k bigger than or equal to big L, S of n sub k is bigger than M. That's right. That's the definition. I might have used different symbols when I gave the definition, but that's the definition. What does that mean? What does it mean to tend towards infinity for sequence we're learning? To tend towards infinity. What did you say? Well, it does diverge, but it diverges in a special way. To tend towards infinity, it says you give me any number, we get bigger than that number. And not only do we get bigger than that number in that sequence, at some point you not only get bigger than it, you stay bigger than it. So, not only are you bigger than it, you're bigger than it for all positions. Yeah, after a certain position. Evan, is that okay? Yeah. Okay. So that's what we want to, that's the definition. That's what we use to verify something. Okay? We can use. It's not the only way. We have facts that we can use to verify things. Okay? That's what I had in mind here as the definition. Okay. Well, so if you give me some positive number, or some real number, m, how do I know that I can get a term from the sequence bigger than it? I don't know. Well, if it's unbounded, that ought to help. The sequence is unbounded, that ought to help me. So here's what I'm going to do. I've got to create, my job is to create a subsequence that tends to infinity. So I got to work on creating the subsequence. Here's what I'm going to do. I'm going to say, well, since S of n is unbounded, and S of n is always greater than 0, then S of n is not bounded above. Excuse me. You know, why am I writing that? Well, look, S of n unbounded, you can be unbounded in a couple of ways. You're either not bounded below or you are not bounded above. But it is bounded below. So to be unbounded, it must be unbounded above. Okay. So that means that S of n gets bigger than any number you give me, eventually. Or at least at some term it's bigger. Well, I'm going to give you a number. So that means 1 is not an upper bound. One's an upper bound. 1 is not an upper bound. Yeah, I'm picking 1. And the reason I'm picking 1 is my job is to create a subsequence. So I'm going to have a term that's S sub n sub 1. The first term of the subsequence. Is that okay? So, okay, well, so 1's not an upper bound. What does it mean not to be an upper bound for S sub n? That means there's an S sub n. There's a guy, a term of the sequence that's bigger than? It's bigger than what? 1. Bigger than 1. Is that okay? So, how can we write down there exists a term of the sequence? Well, we say there's a position, such that the term in that position. So there exists an n sub 1 element of J, such that S sub n sub 1 is bigger than 1. So that's my first term of the subsequence. Is that okay? I'm creating. I don't know why we should stop with just working with 1. We should also work with 2. Is that okay? What can you tell me? S of n is unbounded above, right? So is 2 an upper bound for S of n? No. Also, 2 is not an upper bound. For S of n. So there exists, I'm going to write down n sub 2, element of J, such that I'm going to write this down, but it's not been justified yet. That's the part that hasn't been justified. I'm trying to create a subsequence. So to create a subsequence, you take a term from the original sequence. The next term you take to make your subsequence has to be a term that's to the right of the first term we selected. Is that okay? Otherwise, otherwise what I'm creating is not a subsequence. Is that okay? They got to keep the order. Is that all right? So I'm saying, oh, there's an n sub 2, a spot beyond the first spot that we chose. Okay? Such that S sub n sub 2 is bigger than 2. Okay. I said I didn't justify it. I don't want to justify it here on the principle. The existence of such and n sub 2 is proven by contradiction. What do I mean? Well, suppose that such an n sub 2 didn't exist. Suppose you didn't have an n sub 2. Suppose such an n sub 2 did not exist. What are we talking about? Let me come over here to the side here, right here.
Without being an institute is less than or equal to.
Yeah, it's that part, but just in the whole thing though. So, okay, here's S sub 1, it's the first position. S sub 2, second position. We keep going, we eventually get to n sub 1. This is S sub n sub 1. Okay. And I'm saying afterwards, there's no term, there's no position in the sequence, so that the term in that position is bigger than 2.
And then one would be an upper bound.
Not necessarily n1.
That's the
Well, you're getting close to it. You're getting the right idea. That's beautiful. Okay? Okay. So here's the thing. So if it didn't exist, then here's what I'll say. Then Z is not a good term. T equal to this represents a number. The maximum of the absolute value of S sub 1, S sub 2, all the way up to S sub n sub 1 and 2 is an upper bound. For S sub n. And that's not allowed because S sub n's are not bounded above. Is that okay? So that's the reason behind it. So there's got to be a spot beyond n sub 1 that got bigger, that the term in that spot had to be bigger than 2. We'll go over this. We got time to breathe, relax. Really, I didn't even need absolute values here. It's kind of in lots of proofs we would have absolute values. But I really didn't need absolute values because the terms themselves are positive. That's right. Is that okay with everybody? So a lot of proofs, when we get abstract, not having that positive part would have absolute values involved. Okay? I don't know what that is. Probably aliens. But we don't keep going. So let's go over this just a little bit more. So let's say this n sub 2 didn't exist. So we're just going over again. N sub 2 doesn't exist. That means that every term after here is less than 2. All the terms after here are less than 2. Then you just take the biggest ones of the first n sub 1 terms. You know, there's only n sub 1 number of them. Let's say it's 7. Okay? Let's say there's only 7 of them. N sub 1, 7, for instance. You just take the biggest one of the 7 and 2. And every term of your sequence is less than that. Does that make sense? But that can't happen because the sequence is unbounded. I can ignore it. I don't know about you guys. I don't even have kids, and I have that capability. I don't have kids, but I was one. Okay, so that's what gives the reason for the existence of n sub 2. If I can make that argument every time. So for the number 3, there exists an, say it again, n sub 3. So ladies and gentlemen, I know I get excited and move everywhere. This parenthetical expression is here. That's the contradiction. Dennis, have I hit the spot that you were having difficulty with?
I think that was it, because we were talking about that. And Christie was on to the last night, but we were still debating a little bit.
Okay. Well, good. Good if you make progress. It's not easy, and the hard work yields progress sometimes. We hope, not all the time. All the way to get it. But okay, I'm going to go just a little further. So, what would be next then, Dennis? What would I say next? So, 3 is not an upper bound. So there exists a what? Element of the natural numbers such that n sub 3 is? That's right. Is that you, Alan? Good. That's what it is. And S sub n sub 3 is bigger than? Okay. What would I say next? I'm not going to do 4.
Continue definitely.
Continue this process forever. That's right. Thus, we have created a subsequence S sub n sub k of S sub n. Oh, great. Such that, one more thing, such that S sub n sub k is always bigger than? Nope.
Okay.
K. Who was that? Who said that? That's right, K. Somebody said it. Maybe it was David. But it's K. That's what it is. Okay. I still haven't got it going to infinity. Dennis, I still haven't got the subsequence going to infinity. But there, I've erased it, but it was over here on this sideboard, what it meant to go to infinity. So to show that, I would say it this way. We will show that S sub n sub k tends to infinity. And that's our last goal. We got this subsequence now. I hope it's a good one. Now look, if you created a subsequence and it didn't go to infinity, well, we didn't get the answer. That doesn't mean that our time was wasted. We didn't finish yet. We just tried something else. Does that make sense? But you just keep trying. And sometimes you get stuck and you need a little help. Okay? My job is to be there by the phone or in my office, or to be here now. Okay, now we will show S sub n sub k goes to infinity. And really, what's moving here? What variable's moving?
Okay.
That's correct. That's you, Angie. Good. Okay. Okay, how do I show this? Well, Dennis, what's the definition? I'm going to let something be given. Be a real number. We want to show. So here, actually, I'm using little different symbols to get some different variables involved. I think it was you. It might have been you, Christy, who was asking. It was Christy.
I kind of put a funky symbol in there too.
We want L element of n such that for all little k's bigger than or equal to big L, S sub n sub k is going to be, should be in absolute values, right? Is that what it was?
It's positive.
So it doesn't matter. It's bigger than, oh, it wasn't even supposed to be in absolute values. It wasn't supposed to be in absolute values. It's just bigger than m. That was the definition. Wasn't even in absolute values. Okay? Okay. Well, what do I know S sub n sub k's are all bigger than? K. So if I can get a k bigger than m, do I know? M's a real number. Do I know that there's some natural number out there bigger than that number m that's been given to me? Yeah, that's right. You give me a real number, there's a natural number bigger than it. Okay? Okay. We know there exists an L element of the natural numbers such that L is bigger than m.
Second to last line, is that L element of n the natural numbers?
Yes. Yes. So, yes, it should say J. Who's talking to me? I've forgotten your name. Nat. Nat, thank you. Yes. Thank you for paying attention.
Trying.
Well, that's right. That's all nits can do. I don't know. Sorry. So that, well, wait a minute. So for all for all k bigger than L, bigger than or equal to L, k is going to be bigger than m. Because k is bigger than or equal to L, which is bigger than m. Is that okay?
Yes, and then
That's right. I'll just say it's bigger than him. I hope that's clear. It's bigger than Kay, so it's bigger than him. Okay, I did 3 problems. But I don't think they're easy, and the fact that you probably worked on, maybe I'll say that something's wrong. I don't know what you're doing. But maybe you worked on them, and having worked on them, you were more ready to understand the solutions that I can bring. And I'm okay with that. I'll tell you a quick story. I interrupted when you guys were getting set for the classes, which I know is very important, but they're not as important as my stories. So I'll tell you this story. When I was an undergraduate, when I was a junior in college, I'll tell you this one quick story. I took a differential equations class. We're not done. I'm just telling the story. This is a recipe. Okay? I took this differential equations class, and I had a term of procrastination this time. Okay? And so my teacher was much like I am. His name was David E. Johnson, and Dr. Johnson said, he would teach us a section in the book, do 1 through 41 odd, come home, come to class the next time we had a class period, ask questions about the problems I assigned you. Okay? And then once you ask for 15 minutes, next day repeat. That's what happened. Okay? That's the way I teach. Okay? And I teach calculus, pre-calculus, college algebra. That's the way I do. I'm good, bad, I'm not saying that. That's what he does, that's what I did. That's what he did, that's what I did. Well, I didn't do the homework. He didn't take it up. I didn't do the homework. But every time we had a class period, I said, Dr. Johnson, when you gave a chance to ask questions, I said, Dr. Johnson, would you do problem number 17? You do problem 27? I'd ask one question each class period. And I wasn't trying to take up class time. What my thinking was, I'm eventually going to do problems. And when I go to do them, I want to have more examples to work on. For the first exam, I was 77 mathematical pages behind the night before the exam. Hadn't done a homework problem. I made a 77 on the exam. That's what happened. My thinking at the time was, I wish I'd have been 100 pages behind. See, it totally correlated. That's what I was thinking, why didn't he cover more? So I made 77, and then I thought, I can do better than that, okay? I can do, that's a C. And I said, I can do better than that. I was disappointed, so I got to work. Okay, woke me up, I got to work. I ended up working real hard, and the course was not bad. Okay, it wasn't. You did the problems. You got conditioned to be able to do the problems. He gave you test problems that were like what was in the book. You recognized them. You did them. I made well. I did very well after that. But when you start off with a 77, it's not easy to come back to an A. Okay. Well, I got my grade. I made an A-. So I went to Dr. Johnson. He was a very nice person, and I said, Dr. Johnson, was I close, or were you nice to me to give me an A-? I mean, maybe I had an 88.7. He was being nice to me. John, let's look. John, you had a 91.4. You just start staring at me. 92 is an A. We're talking about, a point or two. That's all we're talking about, the whole term. Okay? I didn't say anything. He's just staring at me. He said, John, I'm going to change this to an A because I remember that you always asked questions. And I said, yes, sir, I worked very hard. And he said, I knew that you were working hard. Yes, you're doing the homework. I wasn't doing the homework, but I sure as heck wasn't going to tell him, and he's dead now. And that's a true story, and that's what happened to me. What's next? What is next?
Question now.
What is next? Okay. Well, let me tell you what we've been doing. Yes, sir, Evan.
We're going to have another homework assignment to do.
Yes.
Have you already covered that?
Yes. So I haven't given out the homework assignment. Did I say we're going to have another homework assignment to do? Yes. Is that what you're asking me?
Yes.
Yes. Yeah, I did say I'm probably going to get it done tomorrow. It's going to be short. 3 or 4 problems. They're going to be basic problems. That's going to be it. Just something about continuity, something about the limits of functions, and maybe 1 or 2 more problems.
Okay, another question.
Yes, sir.
The final exam, are you going to give the study guide?
Yes, I'm going to study that. What did I say? It's not. That's right. And it's not a final exam. Okay, it's test 2. Test 2.
Sorry, I was out of the room.
Yeah, that's right. You asked your question. Well, I wouldn't, I would think. But you never know. Not witnessing. Yes, we're gonna have a study guide. I'll probably give you that relatively early Sunday.
Oh.
Because I'm gonna come to course. I got 2 more lectures, that's it. 32 is on the computer over there to be uploaded. And 32 is, I got started in a proof that was long, that I started about minute 46. And so it ended about 1 hour and 15 minutes. So have some popcorn before you. 32, that I'm gonna lecture on. That's what I did. Okay, what's next? Well, I'll tell you what I'll be something similar that I'll put on the test too, and on the homework to make sure we do, just to be able to do a language problem. I don't know where you are in watching videos now. You don't have to tell me. Okay? I'm not asking you to tell me. But we've got 32 videos about to be uploaded. Okay, so 31's uploaded. 31's uploaded. So the course is going to be 34 videos. I don't know where you are, but that's what's going to be covered. Does that make sense? Okay. All right. So kind of early on, in terms of chapter 4, it has to do with it's the first thing early on. I mean, you can't get much earlier than first thing. It has to do with limits of a function. And so, let's see. What's the definition of limit of a function? This is so peculiar. I can't stand this chalk. This piece of chalk. There. I'd like to write down the abstract definition and then do one for real numbers, but we're talking about real number function where it's not so abstract. So here is the definition. So this is, I would say, recall. It says, given a function F that maps a metric space X into a metric space Y. I didn't say that right. I should say let F be given a function F that maps E a subset of a metric space into a metric space. Let P be a limit point of E. Then the limit as X goes to P of F of X exists if there exists a Q element of Y such that for each epsilon greater than 0, there exists a delta greater than 0 with I'm glad we have something to look forward to with this definition. I would say with, I said where. The distance in X from little x to P being bigger than 0, but less than delta, forces the distance in Y of f of X to Q, the distance between those two, to be less than epsilon. I'd like to do an example, something I'm going to ask you, okay? And I have given this type of example in the video lectures, something just to reinforce it. So, as a quick example, let's let f of x be equal to 14x minus 12. Show the limit as x goes to, let's say 2, of f of x equals to 16. So Tiffany, I'm going to use the definition. I'm just going to highlight this stuff. Well, there's got to be, this is the Q, this is the P. Okay, this is, I miswrote something. I should say, in this case, the limit as x goes to P of f of x equals to Q. I should have added that. I wouldn't get too excited. That's part of the definition. We're defining a limit. Okay, we want to show this. I'm just going to go one more minute. Show this. When's your homework due?
Thursday.
Thursday.
Friday.
Thursday.
Like Thursday by midnight, so how do you?
Oh my God, Allie, if you turned it in Friday, I would take it. If you turned it in Saturday, I would take it. So, I mean, I want you to turn in by Thursday, because here's what I want. I want you to go, because I'm going to give you another homework, and you need to move on to it. And because you need to start studying for the other class, and you need to start studying for the final American test too, okay? So put the deadline on yourself, turn it in for school.
All right.
Would I accept it? Yeah. So this is so here's what I want. So the way we do this is we let epsilon be greater than 0 be given. What we need is we need this delta. With sequences, we've been working with them. We'd be given an epsilon. We need with sequences, we needed an
We needed a big N.
big N. Now we're looking for a delta. A delta is a distance. Epsilon's a distance, okay? We need a delta greater than 0, such that for all x element of, here it's R. R is our metric space, okay? With the distance in the original domain space, which is R, 0 less than, what's the distance? It's absolute value of x minus, I write down P.
2.
Yeah. Less than delta, then that forces the f of x. What's f of x? F of x is,
14.
that's right, minus the q to be less than epsilon. That's what it is. All I'm doing is rewriting this definition with this specific setup. Okay? That's all for our problem. Our metric space is all. So here, what we want is that absolute value of 4x minus 12 minus 16 to be less than epsilon. So we want 14x minus 28 to be less than epsilon. We want, what happened to x? We want 14, the absolute value of 14, times the absolute value of x minus 2 to be less than epsilon. And look, that's what I get to control. X minus 2 is that absolute value. I get to pick the delta, okay?
Okay, stop.
Okay.
Back,
14.
okay. I'm done.
So we want the absolute value of x minus 2 to be less than epsilon over 14. There sits the delta. Delta is sitting right there in front of me now. So here, we let delta be equal to epsilon over 14. Then, for all x in R with absolute value of x minus 2 bigger than 0, okay? And less than delta, we have, so I'm just working with that. We have 0 is less than, x minus 2 is less than epsilon over 14. That says we have, I'll just work with this part. We have 14 times absolute value of x minus 2 is less than epsilon. Bring the 14 inside. We have, so this isn't what we want. This is what we have. 14x minus 28 is less than epsilon. So that means, and that's in the discondition. So we have, here this would be the same thing as 14x minus 12 minus 16 is less than epsilon. And that's exactly what we wanted to have. Okay? And we got it. Excuse me. Thank you. So the limit as x goes to, what was it, 2? F of x, or 14x minus 12, does indeed equal 16. And I'll definitely ask you one like that on your test, and one like that in the homework, and that's the way that it works. And I did one on the video already.
Do we have to have the 0 is less than?
Yes, for the definition of limits. For continuity, the difference between continuity and limits is that you don't have that 0.
When the absolute value of y is.
So here, for this particular problem, it works even when we don't include this part. It still works for when x is
Real.
Yes, that's right. But even when we're talking about limits, we want to have this. The idea with limits is that we want to be able to say for the limit of function to be equal to, we call it q, is that as the input values, the x values, get really, really close to p, they're really, really close to p, they force the output values to be really close to q. But we say that for all input values except for p itself. Remember, we're going to p. Except for p. We don't care what happens in limit, what happens exactly at p.
So you don't want this to be 0.
To be 0. That's why we put that in. Ladies and gentlemen, I've taken up enough of your time. Thank you very much for being patient with me.